All right, welcome. Today, we're going to tackle some seriously cool ideas from a field called classical analysis. We're going to look at how mathematicians figured out a way to, well, tame infinity, using some powerful concepts to get a handle on shapes that are way more complex than you can imagine.
So let's just dive right in with a big question. How do you put a fence around infinity? I mean, it sounds completely impossible, doesn't it? But this is exactly the kind of problem mathematicians were up against. They were dealing with collections of points or sets that could fly off forever or be full of weird gaps. They needed a way to sort out the ones that were well-behaved, and the tools they came up with are honestly just beautiful.
So here's our game plan. First, we'll talk about why infinite sets need taming in the first place. Then we'll build this super powerful recipe for something called compactness and see its wild guarantee with what I call the Russian doll principle. And finally, we'll explore what it really means for a shape to be in one piece by looking at connectedness.
Okay, first section, taming infinite sets. So why do we even need rules for infinity? Well, it turns out that for the heavy hitters of math, like calculus, finding maximums and minimums, making sure things flow smoothly, you can't just grab any random collection of points. You've got to know which sets are going to play by the rules.
Yeah, infinite sets can be a real headache. Some of them just shoot off to infinity, they're unstoppable. Others are kind of like Swiss cheese, just filled with all these holes and gaps. So to build the solid foundation for modern analysis, mathematicians had to create a system to separate the predictable sets from the wild ones. And this all led to two absolutely crucial ideas, compactness and connectedness.
So let's start with what might be one of the most important ideas in all of mathematical analysis, compactness. You can think of it like a master recipe for finding sets that are super stable and reliable. We're going to build up the definition one ingredient at a time.
The first ingredient is pretty intuitive. It's the idea of being bounded. All this means is that a set doesn't just wander off forever. A good way to think about it is you could trap the entire set inside a giant but still finite beach ball. If it fits, no matter how big that ball has to be, the set is bounded. Simple as that.
Okay, the second ingredient is being closed. Now this one's a little more subtle, but stick with me. A set is closed if it includes its own edge, its own fence, so to speak. Here's another way to think about it. If you take a bunch of points that are all inside the set, and they get closer and closer and closer to some destination point, well, that destination point has to be in the set too. It can't be just outside the fence. There are no last-second escapes.
And this picture shows the idea perfectly. Just look at these shapes. The blob, the curve, they're solid. They contain their own edges. They aren't missing their skin, And hey, even that single little point is a closed set, because its boundary is just itself. This is exactly what we mean when we say a set contains all of its boundary points.
Now, for the big reveal. In the kind of space we all know and love, like a line, a flat plane, or our 3D world, there's this incredibly simple formula. A set is compact if and only if it is both closed and bounded. That is it. This amazing result. It's called the Heine-Borel theorem. And it takes those two simple ideas and combines them into one absolute powerhouse of a concept.
So what's the big deal? What's the payoff? Why is being compact so special? Well, one of the most mind-bending consequences is something that I love to call the Russian doll principle. Its formal name is the nested set property, and it gives us this incredible guarantee about how infinity works.
Let's walk through it. Okay, imagine you start with a compact set. That's our biggest Russian doll. Then you put a smaller compact set completely inside of it. Then an even smaller one inside of that one. And you just keep doing this forever. An infinite sequence of nesting dolls. What do you think is left at the end? This is the incredible part. The nested set property guarantees that the intersection of all those infinite sets is not empty. It can't be. Even as the dolls get smaller and smaller, down to an infinitesimal size, there will always be at least one single point that is trapped inside every single one of them. The sets can't just disappear into nothing. Compactness forces something to exist. It's an amazing guarantee.
Okay, let's switch gears and talk about our second big idea for the day, connectedness. So if compactness is all about being contained and complete, connectedness is way simpler. It's just about being in one piece. We'll start with the version of this idea that makes the most sense right away.
A set is called path-connected if you can get from any point A to any other point B by drawing a continuous path without ever leaving the set. It's pretty much what it sounds like. If you're in a room and you can walk from any spot to any other spot without having to jump over a chasm or teleport, then that room is path-connected. And this image just nails the concept. That blob on its own, totally connected. You can draw a line from anywhere to anywhere else inside of it, no problem. But the second you think about the set that's made of both the blob and that separate point, well, the whole thing is disconnected. There is absolutely no way to draw a path from the blob to the point without leaving the set.
But, being path-connected isn't actually the whole story. Mathematicians, of course, needed a more general, more powerful definition of what it really means to be in one piece. And that brings us to the formal, big-picture definition of a connected set.
So let's compare them. On the left, path-connected. We just covered that. You can draw a path. Easy enough. On the right, we have the more general idea, connected. It's actually defined by what it's not. A set is connected if you simply cannot break it up into two separate, non-empty pieces that don't touch. Now, while every path-connected set is also connected, it doesn't always work the other way around in some really weird mathematical spaces. But for our purposes, just thinking of it as being in one piece is totally the right idea.
So, after all that, why does any of this abstract stuff actually matter? Because these properties are the literal bedrock that calculus is built on. Compactness is the reason we can guarantee that a continuous function on a closed interval will have a highest and lowest point. That's the extreme value theorem. And connectedness? That's the whole reason the intermediate value theorem works. The one that says if you draw a continuous line from a height of 1 to a height of 10, you are guaranteed to hit every single height in between. Without these properties, those theorems just fall apart.
And that pretty much wraps up our tour. We started with this seemingly impossible question about putting a fence around infinity, and we ended up with these deep concepts that literally guarantee existence and continuity in our mathematical world. It really makes you wonder, if the basic rules of space have these kinds of surprising guarantees built into them, what other hidden structures are out there just governing our world, waiting to be found?